When we look for the absolute extremes of the universe, our minds immediately go to black holes. We assume they are the only objects capable of breaking the rules of physics entirely. But right before you reach that breaking point, there is a hidden threshold, a middle ground where physical reality stretches to its absolute limit, but manages to hold itself together. To understand this limit, consider this. A single teaspoon of this specific material weighs billions of tons on Earth. This animated scale shows exactly how extreme this gets. We are taking more mass than our entire sun and packing it into a sphere only about 20 kilometers across. You are looking at an entire star squeezed into the footprint of a city. How does an object reach this density mathematically? How does it survive without collapsing completely? To find the missing link, we have to watch a giant star die and see exactly what happens when the universe simply runs out of room. It starts at the end of a star's life. When a giant star burns through its nuclear fuel, it detonates in a massive supernova. The violent blast strips away the star's outer layers, but the core doesn't disappear. Without the outward pressure of nuclear fusion to hold it up, that core immediately begins collapsing inward under its own immense weight. Inward gravity becomes so intense, it physically squeezes the empty space out of normal atoms. Under this pressure, protons and electrons are forced to merge. What remains is a dense, solid sphere made entirely of tightly packed neutral particles called neutrons. That complete structural failure of basic atomic matter is the exact mechanism that gives you a teaspoon weighing billions of tons. That extreme internal density radiates outward, claiming a massive gravitational territory in the space immediately surrounding the star. The pull is lethal. Any object falling toward it would be instantly stretched out and crushed well before it ever hit the surface. This massive density warps space and time into a steep gravity well. Passing light beams bend entirely around the sphere. If you look directly at the front of a neutron star, gravity would actually show you the back of it. A neutron star pushes the geometry of space and time to the absolute limit, stopping just short of tearing a hole in reality. Along with crushing matter and warping gravity, the collapsing core also concentrates kinetic energy. When a spinning figure skater pulls their arms inward, their rotation speeds up. The collapsing star does the same thing to conserve its angular momentum. Because it shrank from the size of a giant star down to the size of a city, this hyperdense sphere now spins dozens, sometimes hundreds of times every single second. This diagram shows a specific type of neutron star called a pulsar. Extreme rotation pairs with an intense magnetic field, capturing ambient energy and shooting twin beams of radiation straight out of the poles. As the star spins, these beams sweep through space like a cosmic lighthouse, making this dead stellar core one of the most powerful continuous engines in the universe. When we detect these sweeping beams flashing across our galaxy, we are looking at an active, terrifying laboratory. Neutron stars act as a universal stress test. They show us exactly how tightly matter, gravity, and energy can be compressed while still existing in the physical universe. But despite all that power, a neutron star sits precariously in a fragile state of equilibrium, balancing perfectly on the razor's edge of physical reality. If this city-sized sphere were to pull in even a small fraction of additional mass from a nearby companion star, the math simply runs out of room. That extra weight breaks the balance. The outward pressure of the neutrons finally fails, and the star implodes forever into absolute darkness, leaving nothing behind but a black hole.